Hello, my name is Ali Robinson. I am a dual degree computer engineering major, senior from Atlanta, Georgia.
And hello, my name is Christopher Williams. I am also a dual degree computer engineering major, and I'm a senior from Dallas, Texas. And this is our final project for our Introduction to Embedded Systems course. In this project, we were tasked to use a Zumo car and demonstrate motor control and driving, as well as light sensor scanning and ultrasonic sensor scanning. This was done by programming the Zumo to navigate to a light source while avoiding multiple obstacles.
For the parts, we used a Zumo version 1.2, which features dual motor drivers, general purpose input-output modules, an integrated LSM303D 3-axis accelerometer and 3-axis magnetometer. It also has a built-in buzzer and headers for the STM32 L4R5ZI microcontroller. Parts that did not include with the Zumo are the distance sensor and light sensor, which we also used, and a red LED.
The Zumo starts with an initial scan for light. When it scans and sees a significant source of light, we remember the direction it's coming from and set our left and right Boolean variables accordingly. And if it doesn't see any significant source of light, it will just move forward. This is a decision we made because sometimes it could sense the light, but the values would seem more like noise than anything. So we decided to only move towards the light if it was above a specific value. If it doesn't see any light, it attempts to go straight down the track until it runs into an obstacle, in which case it will initiate another scan for light and continue to move towards it, after it makes its way around the obstacle, of course. Our goal was to keep the Zumo moving forward while remaining centered as much as possible. The Zumo stops when the light sensor is reading greater than a predefined value and the distance is about 6 inches from the light source.
So the Zumo is scanning for the light source, and it will go forward until it runs to the obstacle. Then it will turn right and go forward again and scan for the light source after it reaches the obstacle, and then turn left to stay centered and go forward again afterwards, in which case we'll run to the third obstacle, begin to scan for the light source, go towards the obstacle.
It turns left because it is going towards the light.
And then turn and go forward some more. It will scan for the light source and then won't detect an obstacle, so it will go toward the light source and stop.
To navigate such a small course, we tried to ensure that our vehicle always made sharp turns so that it was able to get around all the tightly spaced objects. Unfortunately, when our battery power was low, it affected the motor and caused a weaker pulse to be sent to the vehicle. This made the turns less than 90 degrees, and so the distance sensor wouldn't always be accurate because
it wouldn't be coming at an obstacle at a 90-degree angle.
So you have the Zumo and the compass pointing north, and these are the readings. And we take the Zumo, face it south, and these are the readings. Once again, face it north, back up, and we take it and face it south. So the noisy magnetometer, it was hard to get consistent values, and from the Pololu website it says the compass gets a lot of interference from motors, batteries, PCB, and its surroundings, so it's not generally used for precision navigation.
For our emergency vehicle application, we decided to have a change in the Y direction of the accelerometer trigger the LED and buzzer to simulate an ambulance. One of our hardships while doing this was preventing the accelerometer from being triggered during the initial startup of the Zumo vehicle. And that concludes our project. Thank you for listening.